assuming that looking at the topics in the school, by now you would have already realized the nitty-gritties understanding of generative AI methods, foundation model and generative AI methods. Now, I'll take you to something which probably is challenging, is slightly futuristic, and currently the research threads in general in the entire world. In fact, many of the papers that are coming in on these topics, like not dis and no traces, um, are in 2024, 2025, right, and 2026 now. These are very current topics where right now the research community is working on. And as you go along, the first 15-20 minutes of the part of my presentation would actually highlight what do I mean by these two keywords. Um, by now, if all the keynote speakers before me have already must have highlighted that we are in the world of foundation models, right? And when we talk about foundation models, these models are both descriptive as well as generative, right? So within foundation model, these are like two different categories of foundation models. One are discriminative foundation models, and another are generative foundation models, like classification based as well as generative approaches, where you can ask the model to generate newer samples, be it text, be it audio, be it video, right? And both the kinds of foundation models, they actually follow these four broad categorization, subcategorization. Like some would be language models, Professor Modi must have talked about the LLMs in the law domain, right? So there's like language models where you are giving in questions in text and getting response based on the textual information. Those actually, all these kinds of language models, or very broadly called as LLMs, large language models, right? The second category is where you have essentially an image as an output, right? So you give input and image and output, you obtain an image as an output, or you provide image as input and then you obtain classification outputs as outputs, so depending on whether it is generative model or discriminative model. Similarly, the third category is audio models, where you're processing audios, be it like in a discriminative mode or generative mode. You are at the end of the day processing or generating audio samples. And the fourth category, which is very popular, in fact, if you're looking at Gemini, ChatGPT, these models are in today, in true sense, they are multi-model models, where they're processing different modalities, be it language, be it vision, be it audio, right? It's a combination, a joint understanding of text and vision, text and audio, video and audio, right? So all these integration of multiple modalities essentially are covered under multi-model foundation models. And again, these are discriminative models as well as generative models. Okay, so again, this is just a precursor of what you may have already studied so far. And models are actually very, very powerful. And one of the very popular multi-model model is Sora, right? Again, by OpenAI. And here in Sora, what we do is we provide a prompt, and Sora actually generates, the platform generates a few seconds of video. And here are two examples that I have created. The first example here, like the prompt is a realistic vintage style fashion model walking in Delhi during golden hour, dramatic light rays casting from the side in silhouette style, wearing a vivid red retro dress, blowing in the wind, holding a black handbag, cinematic lighting, soft haze, red fort in the distance, moody warm tone, shoddy depth of field, 135 film look. So this is a detailed prompt that you can provide to Sora, or for that matter any multimodal model, and you would actually be able to generate a few seconds of video, very highly realistic video, right? It, for the naked eye, for the first time, if you're seeing this, you may have a hard time understanding the distinction between what is real and what is not real. And if I take a look at the exactly same prompt but just change some of these minor variation, like make some minor variations like Delhi to Jodhpur, retro dress to sari, right? Black handbag to colorful handbag, right? And in place of red fort, Mehrangarh fort, which is actually in Jodhpur. The exactly same prompt with these minor modifications, we can generate another video altogether, right? And these days, in fact, AI generated movies, AI generated series are also actually now coming up on a regular basis. In fact, some of the TV channels are already broadcasting those. And while that could be a positive application, the negative applications of deepfakes are also there, where now people are generating deepfakes using the same technology. And Google Nano Banana, which came recently, is also like another multimodal foundation model, which can actually do wonders, right? And which is actually doing wonders. You can actually put yourself next to your king, your prime minister, even India's prime minister, or even Donald Trump, if you wish so. Right? Or I can actually make my German Shepherd pet a super dog, and make him fly anywhere he wishes to, right? So these are actually very powerful models, both in the image domain, text domain, audio, as well as multimodal domain. Right, and so far, again, like just connecting back to what you may have already studied in terms of the foundation models, the whole procedure of training them, and then how actually they have evolved. Uh, One very basic fundamental concept is that they are trained on a huge amount of unlabeled data sets, like Line 5 billion dataset has images or samples which are actually 5 billion, right? So there are many datasets which are like a couple of trillion size datasets. Few petabytes of datasets are being used to train these foundation models. If you means while there are no official numbers with respect to how much training data has gone in terms of training a ChatGPT 5.2 model, the most recent one that is going on right now. But it is estimated that they have trained on few trillion samples to understand. And again, these samples are all three modalities: text, video slash images, and audio samples. Right. So it's just like a huge amount of training data, and it requires thousands and thousands of GPUs. Means again, it is estimated that they have used 300,000 GPUs to train the most recent foundation model, right? Which we are using probably free of cost. And these models, the families, essentially, again, either they are based on transformer based, diffusion based, and auto-regressive models, and so on and so forth, right? And then even the large classification models are also now considered foundation models. And once you train a foundation model in a self-supervised fashion uh, on a very large corpus data without any labels, once you have kind of understood or the entire knowledge space, you can fine tune for different downstream tasks. You can do prompting to interact with the foundation models for specific tasks, right? I can take a particular model, let's say Llama model, and do a fine tuning process and do it for medical diagnostic purposes, right? Or I can go on ChatGPT or Gemini and write a prompt and instruct the model to generate a particular output or do a particular task, right? So these are like different ways of interacting with these foundation models, and they're very cost effective in terms of, in place of training small multiple models, one model per specific type. Now you can have very big models, and then multiple applications can be in a cost effective fashion can be actually built. And that's what has actually is happening in major cities like Bangalore, Hyderabad, or even actually San Francisco in the Bay Area, right? And there are four kinds of foundation models. One is encoder only foundation model, like BERT, which has a very strong representation for classification settings, discriminative settings, or retrieval settings. The other kind of foundation model is decoder style or GPT style, which are autoregressive, and they actually provide you reasoning capabilities. The T5 kind of model, which is encoder decoder combined, like sequence to sequence modeling kind of applications are built upon encoder decoder model. And DeepSeek actually follows another paradigm called as mixture of experts, where you have multiple small models. Individually they may not be considered as a large foundation model, but these small models, when combined in a mixture of expert fashion, then they can be considered as they are considered as a large foundation model, and can do actually multiple um, tasks, and requires many levels less, or many tiers less. And that was the DeepSeek movement that happened last year. Right. So this is again like a broad understanding about broad diagram of that you train a transformer model, which is encoder and decoder combined jointly, like where you start with the input embedding, with input, and encoder encodes the features, and then at the time of decoder you obtain a particular output, right? And once the training of encoder decoder, joint training of encoder decoder happens, you can stack multiple encoders that actually becomes BERT. If and like combine them in an architectural fashion, that becomes BERT. If you stack multiple decoders, right, and then in an architectural fashion, then it actually becomes GPT. So these two essentially are broad categories of two foundation models, where based on the encoder and decoder um, uh, configuration, where the training objective of BERT would be one of the training objectives, or the loss functions would be masked language modeling, whereas GPT would actually focus most on auto-regressive language modeling, right? So this is again like the two categories of BERT and GPTs, but again like they are based on encoder and decoder style architectures. And the combination of encoder decoder kind of T5 kind of architecture also exist. And as I said, like DeepSeek actually goes with slightly different approach of mixture of models. Now, so this actually whole area of foundation models and generative AI has actually caused two basic fundamental and again, like we were using this textbook on pattern classification. I'm not sure how many of you know about that book. It's a classical book, and the two pieces of conventional wisdom that were actually taught and kind of transfused into our blood was that if you provide garbage data, like unlabeled, not cleaned, dirty data, you will get actually very poor performance. Like your classification output, or your dimensionality reduction, or like supervised, unsupervised, all sorts of learning mechanisms would fail. Right. So that's why like we used to call it the garbage in, garbage out. If you provide garbage data, you'll get garbage output. However, if you look at now the basic premise of foundation model, you're providing billions and trillions of data samples. And it is not necessary that these data samples are clean, right? These are like web scale data sets or web scale samples. And therefore these samples are not cleaned. Probably some adversary may be actually giving some random samples to fool the system, right? And therefore it's in true sense, in a classical sense, it's a garbage data, right, without labels. But foundation models are still able to, in a completely data centric fashion, is still able to utilize this huge amount of data and have the world's knowledge, when so-called world's knowledge, right? While it is still not following the entire world's knowledge, and we'll see, we still face a huge amount of problems, but then still actually it is able to make sense out of that in a classical way. This whole premise, the conventional premise that you'll provide garbage data, you'll get garbage output, is no more valid in foundation models. in foundation models, every data is important, every sample is important, and you have to provide as much as you can. Right. So if someone asks me that how much data is required to train a particular foundation model, or how much data is required to do this particular task, we always say that there is no limit. The more you provide, the more actually better we can do. Right. So that is now a basic premise. The second, conventional wisdom, again, we were taught to kind of to a level where like we always actually followed that design a model, design a machine learning model which has less number of parameters. Right. So we used to like at least in my examination vivas, even comprehensive exams during PhD. I remember I was asked a question that you have two models, one model with 500 support vectors, and another model which actually obtains only 100 exactly which model actually you would, right? And one model again, the 500 model, let's say 100 parameters to tune, whereas 100 support vector model needs only 5 parameters to tune. Right. So while one is essentially with respect to the dimensionality of the model, the another is the number of parameters that you have to fine tune the model. And at that point of time, our answer used to be that a model which has only 5 parameters is preferred if the performance is same. Right. If the performance is beyond a certain threshold, model with less parameters still performs well, we should take that model. Right. So that was our earlier, that was our understanding, or even actually the community, the machine learning community used to follow that too many parameters leads to overfitting. In fact, there is a theorem called as or a razor actually called as Occam's razor. How many of you have heard Occam's razor, by the way? Anyone from the class, have you heard of this term Occam's razor? I hope I'm audible. Roshni, I'm audible.
Yeah, you are audible,
Huh.
but
If no
I
one
don't
has
know. The
heard,
mic is on at the venue.
okay. There is no way that if not, then I can continue and I can explain what Occam's razor is. Okay, no worries.
Yeah, maybe we can take the questions at the end, but I'm not sure about right now.
Okay, sure, no worries. Let me actually go back to my slide. So says that if you have a model which has less number of parameters, so you always prefer a model which has less number of parameters. So you can actually understand Occam's razor in this particular with the statement. If you have to design a particular model which requires many parameters, and if the same task with same performance can be done with less number of parameters, you always follow the model which has less parameters. That was essentially, I mean, that's a textbook theorem. Right. So we were taught about that we should be ensuring that over parameterization doesn't happen. It was a major concern. But if you look at the foundation models today, the bigger the better, right? So that's what people actually ask. Have you tried, like, if I go and tell, actually, let's say in one of my research papers that I have only tried a 3 billion or 7 billion parameter model, I'm pretty sure like the reviewers that why didn't you try 50 billion? Right. So it's right now the understanding is that larger the better. Therefore, the large models like they can incorporate, again, in order to incorporate the words knowledge, you that means that you have to incorporate many functions, and some of the functions are very complex, and they can still be generative or even actually discriminative. Even if you have randomized labels, the model still actually understand the knowledge space and can do wonders, right? So that is that has changed in the last 20 years or so, that you don't have to worry about less number of parameters anymore, and right now more the better, right? Bigger and the heavier model the better. So more data and bigger model, and that's where the world is moving in terms of throw in huge amount of data and have lot many parameters, much deeper network, and you should be able to do better, right? So far what I've talked about is that everything is good, right? Right. And there are many challenges still. It's not that the generative AI or foundation models are completely solved problem, and that's why I call it as a Gen AI paradox. That Gen AI has, or foundation models have both positives and negatives. It is, while it is solving several social good applications, ease of AI application right now. Even an undergrad, even a class 10th or 12th student can also actually do many good things, can think of solving some real world problems, but at the same time it also gives power, unnecessary power to people to actually create many misinformation or privacy safety issues, right? And that's what we'll be discussing about, like what are the shortcomings or limitations of current models, and how actually we can fix some of these things, right? So we'll understand some of these things with certain examples. Okay, so now just imagine, just close your eyes for 10 seconds, and imagine that you are thinking of image of a house in Nepal, right? So I'm assuming most of you are from Nepal. So if I ask you that, can you imagine, or can you generate, or can you draw an image of a house in Nepal, you can close your eyes and think about it and immediately actually imagine that, right? Now if I give exactly same prompt to our popular models, see what happens. So these are the four outputs. This like yesterday, sorry, day before yesterday, when I was putting up my slide deck, I generated from four popular models like Gemini, DALL-E, Flux, and Llama. Right? These are again very powerful models doing awesome, right? And now you have to tell me, those who are from Nepal, is this the true representation or the only representation? Like I tried generating multiple times, and almost every time I was getting actually similar information. Are all the houses in Nepal like this only? Like, so that all the four models are providing these similar looking samples? Maybe Roshni, you can respond. Like all the houses look like this only in Nepal,
No, of course not.
right? So this is from Nepal to India, and actually nothing changes much. So to these foundation models, countries like India, Nepal, Bhutan, Bangladesh, Pakistan, means our Indian subcontinent countries, they are kind of poor countries, right? And then the houses actually look very old and not to their likings. But at the same time, if I simply say that a house in Washington DC or house in London, you would actually see very fancy houses. Right? So that's a huge gap, a disparity, or what you call it as a bias, um, against or towards a particular community. Right. So this is a huge problem. In fact, this is an example of Sora that I tried. Means while it is depicting nicely at the backdrop, the mountains and snow-covered mountains, it looks very nice. Like the images are good in terms of the generation quality, but it's not a true representation. That not all houses are like this. That every time you're looking right. So and no good houses or no modern houses. I'm pretty sure King's Palaces and many other houses in Kathmandu are much better than this. And those representations are not being generated by these models. Now, another question: if I run these three videos, think about which of them are actually real and which of them are not real or fake. So this is a major problem. By the way, since I'm not able to communicate to you directly, to provide the answer, all three examples are actually fake examples. In fact, the third example that you saw, the lady with red dress, it said actually all three are Instagram handles, but the third Instagram handle, or the third example actually comes from Instagram handle, which declares that all the content generated, whereas the first two samples actually coming from Instagram handle where they are not declaring, but evidences to show that they are creating deepfakes from different Instagram handles and changing the faces, because we obtain the raw sources also, the source videos from where actually they took these those base videos and swapped the faces. And to my disbelief, the likes, like Instagram has likes, right? So the likes on these samples are in hundreds and thousands. Means the first two examples have more than 500,000 likes, like half a million likes. The third one actually crosses more than a million likes. If I post something on LinkedIn, or if I post something on Instagram, I have never gotten likes more than 1,000. Right, so maximum like 1,000, 1,500 likes that I have ever obtained for one of my posts. Whereas these AI generated content are creating, like, and then these Instagram or Facebook likes, they generate money for the creators, right? So someone else has created certain content, and now you are actually by beautifying it, or doing, like, creating a deep fake from those, and then you start earning money. So those are models, and not giving the due credit. So there are many issues because of deepfakes, be it elections that happens, be the social media campaigns that are there, or information or misinformation on social media. Deepfake has become so common and so popular that you can now generate deepfake content within like 5 minutes, and you don't need to know what is AI, or what is foundation model, or what is generative AI. Right. So in Indian election, we processed more than 3,000 deepfakes last year. Right. So we had to on an emergency basis, we had to work on almost daily basis, that we were obtaining, like we were getting hundreds of deepfakes on a daily basis. During Operation Sindoor that happened last year, we saw a huge amount of deepfakes that came in around that time frame. Right. So this has actually become a huge problem. While it has many positive scenarios, like Shah Rukh Khan doing a Cadbury ad, or ad for local vendors, but that's a positive. But at the same time, these are negative applications. Right. Now, again, I'm just going to run two audio clips. I've shown you two video, but I'm going to run two audio clips and listen to these audio clips. It's a Turing test, right? You have to tell which of the sound, either sound one or sound two, which of these sound are actually real, and which of them are actually fake. Which of them is fake, right? So that there is a one sound is real and one sound is not real, right? It's fake. So I'm going to run these two, and then you can think and imagine yourself, and then I'll tell you the answer after giving you a couple of seconds. So here is sound one. Sorry, what happened? तेरी शान पे सदके कोई दंड है क्या तेरी धूल से बढ़ के तेरी धूप से रोशन तेरी हवा पे जिंदा तू भाग है मेरा. So this was sound one. Now this is sound two now. तेरी शान पे सदके कोई धन है क्या तेरी धूल से बढ़ के तेरी धूप से रोशनी तेरी हवा पे जिंदा तू बाग है मेरा मैं. So I'll pause here for a second, and those who are in online mode, they can also respond. Um, which of these two sounds sound real or fake? So they both are actually from a movie here in India. Not both, means one of the song is from the movie, original singer, and second was AI generated. Same lyrics, same background music, just the artist were changed or swapped. So to give you the answer, sound one, which is in the sound of Mr. Atif Aslam, did not sing this particular song. So therefore, sound one is a AI generated song, whereas sound two, which is actually the original track sung by Mr. Arijit, is actual song from the movie, right? And it took us like few minutes to actually create sound one two. What we needed is like few samples of Atif Aslam, few songs, understand the sound qualities of Mr. Atif Aslam, and replace Mr. Arijit Singh's voice with Mr. Atif Aslam's voice. It just took us few seconds to create this particular example. So right now means when there are applications which can which you can use to have any song in your own voice, right? Or in fact, there is a application called as Suno, right? Suno.ai. If you go there, you can just write prompts. It can give you lyrics, it can give you music, and it can actually create an entire song for you, sung by an artist of your choice, in fact your own voice, right? So the free version may not actually allow all the features, but the paid version actually allows you all the features that actually you can think of. While there is a court case going against Suno that they are infringing copyright law, and that's where like the next part of my slide deck is going to be. But that's what happening. It's already happening. So these are this is the power of foundation model, but at the same time misuse of foundation model, right? And that's what actually brings me to this particular point of that why Suno is facing this particular lawsuit, or even OpenAI is actually going through a lawsuit by New York Times, that when you are training the data on millions and millions of samples, or even billions and billions of samples, you are essentially scraping the web. You are getting the information from the web, and it is not necessary that the model is learning things. Model may be just remembering, right? It may be just doing rote learning, and like the students do, right? Means if you're giving exam just before one night of the exam, right? So what do? You go and mug up the whole examples or definitions, right? You just remember everything. You just sit down and repeat 5 times, and then it just imprints in on your brain. And next time when you see the exactly same definition or exactly same example, you just imprint it back, right? Or and so that these are the problems that while you are not learning, you are probably memorizing the data. Same problem happening with respect to these foundation models. And here is an example of stable diffusion, which is a diffusion based generative model, image generative model, trained on line a mash database. And when prompted, it actually generated very close looking outputs. So this essentially shows that the model kind of remembers from the memory rather than in the learned knowledge space. It's not, you're not creating a new knowledge, because conceptually you should be creating a new sample, right? If I provide if I provide the particular prompt, you should generate rather than just memorize and reproduce. So this looks very close to reproduction based on the memory rather than the learning space, right? And just to again like emphasize or impress you upon that, this is real world example of ChatGPT 4 and New York Times. So New York Times has actually sued, it has taken OpenAI to court, highlighting many of these examples, and this is one of the examples, saying that Here is an article from New York Times which has exactly same paragraph. Just not, it's not a coincidence that one word or two words are copied or one sentence is copied, right? It's paragraphs are copied, and when ChatGPT is prompted to generate a particular news or generate a particular piece of text, it provides exactly verbatim, word by word, exactly same thing, right? And that's where New York Times claim is that you have obtained our intellectual property and built a model on top of it and earning money, whereas New York Times is not getting that. I'm sure many of you have used Chat GPT or these kinds of model to create Ghibli images, right? So when you are doing that, you're essentially providing your sample to this particular these models, and these models learn on your trainings on your data. So tomorrow, if you're seeing your own from these models, that's what actually it's a memorization then generate, right? And this is a huge problem that the research community is looking forward to solve, right? In fact, the Indian government is actually very solve having memorization rather than actually having a generalization problem. And even if you actually learned a bad knowledge, how do you forget that bad knowledge then, right? And this is again like another example that generalization could be unwanted, like not safe at work content, NSFW content can be generated, let's say nude photographs. Now, so if you ask Grok, and Grok has been misused heavily on this side, on this part, that if you ask Grok to generate someone's nude photograph, it would immediately generate it. It will give you warning, but it will generate. While the creators of Grok may not have given the nude data to create the sample, but it may have given a lot of data to train, which may not be nude, but some paintings are there, right? So many of the old paintings from European countries are essentially nude paintings. From there, it would have understood the class category of nude, and because it's like mapping also, like mapping of different one another, it could actually map that nude concept to actual human beings, right? The real human beings. And therefore you could actually misuse this kind of generalization. If there are generalization, then one can misuse these generalizations. Similarly, like I talked about Ghibli, I talked about many other like a song, that copyright issues are also actually showing up. um, and these copyright issues has prompted many celebrities around the world to take to copyright their voice, copyright their face, copyright even their walking style, so that these models can't use their data directly. Like Mr. Amitabh Bachchan and Mr. Anil Kapoor has copyrighted their voices, so they can't use their voices directly. Similarly, like many offensive content can be generated and can be used to mislead the population based on like again deepfake misinformation generation can happen. You can generate samples which essentially represent domestic violence or even hate crime. I've seen many cases where people have used the foundation models, generative models, to upload their photographs and ask to generate a domestic violence output, like output after domestic violence, and use those photographs against someone to go to court, right? Similarly, like ask someone to actually like ask a model to generate a output or sample which represents hate crime, and use those samples to go to court. In fact, we also saw one very interesting case. Like there is these websites called like shadi.com, matrimony websites and all, right? So there you upload your photograph and apply filters and create beautiful or handsome, depending on your gender, like you create those versions which can fool the person, the next person who's seeing your profile, right? So these kinds of outputs may not be wanted, and therefore these are essentially challenges we are facing in the foundation model, right? Now, another example, can you think of what's wrong in these images? I'll just pause for a second, and highlight you what with two examples. Look at this example, third example, a cricket ground with unbowled overs, while where the stumps are unset and the pictures are and the pitches are unmoved. Right? It's a cricket stadium. Like it's an image of like a prompt to generate a cricket stadium where stumps should not be moved. Means there should be more grass, right, on the pitches, and players should not be playing. Like no bowler should be bowling. Now, if you look at GPT, Grok, and SDXL, these are three foundation models, image generative foundation models. GPT, while followed that no one is playing, but the pitches are moved, like pitches are set, and the stumps are also set, and stumps are put in at the right place. Right. So these two instructions are not followed. Right. Same actually goes if you go to Grok. The stumps are not set in the correct location. One of the stumps are not set in the correct location, but the pitches are moved. And SDXL essentially forgets everything. It has just assumed all affirmatives and did not follow any negative sentences, negative words. If you look at the very next, a florist greenhouse with unarranged bouquets where the stems are untrimmed and the vases are unfilled, it did not follow any of the instructions. Right, the vases are filled, the stems are trimmed, and the bouquets are arranged. Right, this is a huge problem that models don't follow the negative instructions. And it's very important actually, again, when we reach to that particular point, I would highlight again that these are providing negative information that this should not happen. Is like in your prompt, like if you say this should not happen, I should not be there, but the sample actually puts you, or the model puts you there. So these are negation, and a negation is a huge problem. Negation prompts are a huge problem for the foundation models. Right, and this is again like Nano Banana output that we created when Nano Banana was launched, and it just simply did not follow the instructions. Right, so now if I again like ask about one more example, imagine like if I have to create an image of 25 famous Oscar winning actresses, or create an image of 25 famous Oscar winning actors. Right, I can give about any of these kinds of examples, right? So this is an output. Again, Google Nano Banana. If you count, these are not 25, right? So these are not 25 people. Okay. Now, if I give one more extension to the prompt, generate an image of 20 male and 20 female Oscar-winning actors. Each of them are sitting gender-wise, alternative manner. Means one male, one female, one male, one female. 20 are sitting and 20 are standing. So this is a much more elaborate prompt, right? I ask, so essentially we need to create 40 different faces, right? 20 male, 20 female. These are not 40 images. In fact, these are not 20 female faces, right? And not 20 are sitting, right? It's barely 8 are only sitting, and the remaining are standing. Right? So this is another problem which the models actually face. This is called as spatial understanding. Right, so these are the issues, the two broad issues that I'm going to like talk about in the rest of the presentation or rest of the session is bad knowledge in the memory, right, or incorrect compositionality structure. Right, this example is essentially it has created an image, it has generated an image, but it is not following the correct composition. We ask specific details to be created, like specific composition to be created, but it is not following that particular composition. Be it the cricket example, florist example, or this example, this is essentially incorrect composition, right? And the memorization, the bias, and all these things are essentially called as bad knowledge in the memory or incorrect knowledge in the memory. And the remaining part of my talk is with respect to focusing on these two topics. So till now, are there any questions, doubts? Um, I can take that up before I move forward. Any questions, doubts? Okay. So then let me move to the next phase of the presentation. We'll again keep maybe it'll last 10 minutes as for Q&A again. Let me move forward then. Okay. So yeah, so the part one or this particular part is going to be the unlearning problem. Okay. So if I'm actually working on a computer, right? If I'm, let's say, working on a doc file, and I start typing, I say I have made, and then accidentally hit the button enter, and and then actually continue typing a mistake in typing. And then I realize I have made a mistake, right? Once the sentence is written, and then I realize, oh, sorry, means I have made a mistake in typing should be a single word, it's a single sentence. What should I do then? Should I just remove everything and then restart? Or I would simply do a control Z, right? I'll and put it and reach to the point where I made a mistake, right? And then continue from there, right? So this is like a control Z button that we use to undo a certain things which we should not have done, right? Or we should have corrected. So similarly, the same concept should actually be applicable in the foundation model. Like we learned certain, let's say, bad information, be it house in Nepal, right? The example that we discussed, or even the memorization problem, or even when you're providing Ghibli your own face image to generate Ghibli output, but the model is using it to generate to learn the next set of version, and then you ask that, hey, that was a mistake, I should not have uploaded my photograph or anyone's photograph for that matter. Can you remove me? Can you do the control Z on my that particular instance? How do I do that? And that's what control Z of AI is called as machine unlearning. Okay, so this is the first kind of uh, thread that is happening in the community, in the research community, where we are trying to enable the model to selectively unlearn certain concepts if we had mistakenly learned incorrect knowledge or bad knowledge, right? So unlearning, model editing, these are actually the topics which are right now being worked upon in the last couple of years. We have been working on, they all have been in the research community have been working on to enable the model to do better, right? And fix the mistakes without the need of retraining the entire model. So again, I'll take you to the first few lectures of that you might have done, that we are learning a network, right? So basically what happens, you have a text prompt, right? A cat sitting on a couch. You have an image that is available to you for training, cat sitting on a couch image and the associated label. Using a huge amount of training data, let's say 5 billion line, 5 billion data, 5B data set. From this huge amount of training data, which is paired, right? Text, prompt, and image, you train a model, a generative model. Like you encode the text embedding, you encode the image embedding, and thus generate an image output, right? Now, once you have trained this particular huge model, at the time of inference, you can provide a particular text prompt, that image of an Indian house. By the way, this is an output that we obtain when I give image of an Indian house, which again is not correct output. But suppose we get this particular image of Indian house, or the correct output we get image of a dog. So when we say image of a dog, we get a dog's image, right? So this is at the time of inference. Training requires data, which is like text and image paired data, huge amount of data to train the model. And once the model is trained, I can give any prompt, need not to be exactly the same prompt that I have seen. I can give any prompt and it should generate a particular output. Now, since a model has not understood Indian house correctly, I should be able to fix it. I should be able to say, hey, this is not the Indian house. Forget this kind of Indian house, right? So how do I actually enable the model to suppress this knowledge or forget this knowledge house and later on add new knowledge. Or if you don't need to add new knowledge, so be it. Right? But then forget this kind of Indian house. Right? So this is what we are trying to do. While the model text to image generative models like ChatGPT, Gemini, they understand and can do um, and generate new samples based on whatever prompt you provide the model that now forget dog. Next time when I give a prompt that generate an image of a dog, I should not be able to generate dog's image, but I should be able to generate cat's image. Okay, so this is the problem of unlearning. So can we forget a particular concept? Can we unlearn a concept in a text to image generative models? So how do we do that? How do we achieve that? That's what we are going to talk about. Right. So let's understand this bit a bit more. I will not go in very mathematical details, but at least give you a broad understanding of what's going on over here. So think of a generative foundation model, right? So when we are training, it has all the data sets, all the samples, the knowledge that is good and the knowledge which is not good. Let's call the good knowledge as a image. So D of retain as all the samples, set of all the samples which are good knowledge. We should not forget that. But do you forget is that bad knowledge, a bad sample that we should have not learned in the very first step. But since we have learned now the model on that particular set, in later stages, how do we forget? So originally your data set is D, which essentially is a union of the two sets. Now, I learned a particular model, like the original training sample that we have, right? The contrastive learning, probably you may have already discussed in this particular school, that over a loss function on the entire data set D, you generate a particular foundation model or all the parameters like theta star, you obtain theta star or the model trained model, which can fit which can give minimum error on this entire data set D, right? Which is a union of retain set and union of and forget set, right? The good knowledge and the bad knowledge combined, you have trained a particular model and obtained a model called as theta star. Fine. Now, our objective is that theta star is obtained with both D retain and D forget, like good knowledge and bad knowledge. But now, since we have figured out that we have certain bad knowledge, I should not, I should obtain a particular model which is not trained on D forget. Right? Bad knowledge should not be used to train the model. So ideally, what should we do? In a very simplistic way, means forget about machine learning. If we know that means our data set has two parts, that it's a good knowledge and a bad knowledge, good sample and bad sample. I should segregate them. I should remove the bad sample and retrain the model. Like, fine, let's go ahead and only use the good data set, good part, and obtain a theta star, which is a new model, different than theta star. Obtain theta dash, sorry, not theta, obtain a new model which is theta dash model, which is trained only on the good knowledge or D retain. Fine. Now, this looks very simple. Where is the research question here? Why this is a problem? If I have to do the same task for every request, let's say if ChatGPT has to do the same, has to entertain same request every time. Let's say you uploaded, every student in this class has uploaded one Ghibli image. And day one, first student says that remove me from the data set. Day two, second student comes and says remove me from the data set. Day three, student comes and says remove me from the data set. So ChatGPT cannot update the knowledge every day. Fine, means you just collect all the samples for let's say 15 days and then forget and then retrain the model after 15 days. Remember, ChatGPT requires more than 200,000, more than 2 lakhs of GPUs to train a particular model. Now, if I remove your data, just fewer samples from the data space, and have only D retain, which is a good model, so-called good model, and obtain, I need to burn so much of power. Now, what happens on 60? It will come and say remove from the data set. Now I'll have another set which is D retain, and then a small subset removed from D retain, right? The bad knowledge. If I do this every time, it becomes very, very costly it's costly to train. So training these large models, because they are very heavy and trained on a large amount of data, is expensive. It requires we of a particular. Now, if you just do a simplest way of forgetting, like removing the data and retraining, is not cost effective. It cannot happen, right? So then, can we on the fly, while the model is getting used, the target is, can we have a particular mechanism that we don't need to retrain the model on the retain set, but still, like from the forget set, drop all the concepts from the model space. From the data is very easy, I just have to delete the data, but from the model also I should be able to delete. The objective should be that this mechanism of not needing to retrain the model, the output obtained using this mechanism should be same as if we had trained on the retain set only, right? The model that we should obtain after unlearning should be same as if the model is trained on retain set, right? So yeah, so I should obtain theta dash without the need to retrain the model by just dropping fewer samples. Now, one can ask, how can we do this? And there are actually some approaches that people started working on, and it's a very new area, like this 2 years, 2.5 years old area. People started working on very simplest. First approach is fine-tuned. Fine-tune the model on the set which is forget class. Now, when we learn, what do? When we are learning a model, we are doing contrastive learning. Like, means, let's say, think of a simplest way of gradient direction, right? So if you're learning in the positive direction of gradient, right? What you have to fine tune with the forget class? What you have to do for the fine tuning with the forget class? You have to go in the negative side, right? You have to forget. You have to, in place of saying uh, W new is equal to W plus delta W, right? You have to do W new is equal to W minus delta W. You have to remove that much of weight on that particular sample. So people actually used fine-tuning mechanisms by adjusting the parameters, which maximizes the loss of forget set. So again, in a simplest sense, here, if you look at the loss function of theta star, we are minimizing, right? So minimizing the loss for the fine-tuning on the forget set, we have to maximize the loss on that set only. So the understanding is that you are not forgetting anything on the D retain or the good knowledge, and only the fine-tuning only on those samples which needed to be dropped, right? And for that you do maximization of loss for those samples. So the hope is that when you do this, you would actually drop only the bad samples. But what ended up happening is catastrophic forgetting. That if I'm forgetting dog, then I may start forgetting wolves also, right? Or foxes also. So if I'm forgetting cat, I may start forgetting tigers also. If I'm forgetting, let's say, hibiscus as a flower, I may start forgetting, let's say, cauliflower. So those things start actually. So that's called as catastrophic forgetting. We forget some other knowledge also. People actually proposed distillation, like you have a large teacher model, and then you funnel this whole thing to the whole knowledge to a small a student model by training on D retain. But remember, D retain is a very large set. So when you are doing this particular knowledge distillation that is also not cost effective. Okay, few people actually did some closed form adjustments of attention layer or latent space layers and in knowledge editing space, but again they are very computationally expensive. And knowledge editing also actually suffers because of catastrophic forgetting. Like you are editing certain knowledge, but then the circuit actually breaks down, or the circuit actually gets confused for similar looking objects. So we have actually proposed two mechanisms, and we have created essentially two subcategories of unlearning methods, like parameter efficient, like only using small auxiliary module, and continual unlearning, like all these previous methods just focused on one concept forgetting. But then this is not how the unlearning should work, right? Today we unlearn one concept to unlearn, tomorrow it can be a second approach, and so on and so forth. So we started actually working on, we proposed a term called as continual unlearning, that we can do or we can unlearn in a continuous fashion. So I'll talk about one of the methods here first, and then hopefully that will make you understand a bit better. So let's understand this particular example. The top example, the top concept says that golf ball, right? Now, a model which has been trained, let's say stable diffusion model, I can very well actually generate a golf ball. I can generate a tennis ball, a soccer ball, basketball, baseball, rugby ball. At the same time, I can also generate a dog breed called as corgi. Fine. Model can do wonders when these are the outputs created by stable diffusion 1.4 model. Now, if I ask the model to forget golf ball, what is happening currently? Like, this is again highlighting back to your my point on catastrophic forgetting. Because all these are balls, right? Very related to golf ball, even tennis ball, soccer ball, all these are very related to golf ball. And tuning in the similar ping pong, basketball, baseball, all these kinds of balls, actually, you also forget those things. See, while my instruction was to forget only golf ball, but the models actually forget, and these are the examples. If you see, uh, um, just below the fine this tennis ball, you see that the two rows highlights that the existing models simply forget all the related concepts, right? But while they can still remember the corgis, right? When they can generate the corgis as a dog breed, no problems. But conceptually, I should not be forgetting tennis balls. I should not be forgetting soccer ball because I specifically asked to forget golf balls only, right? So this is a major problem which the models are facing, and that's what called as catastrophic forgetting of fine-grained classes. Now let's understand fine-grained. What do we mean by fine-grained? The classes which are related. Another example. If I say, means I'm sure all of you know German Shepherd dog and Huskies, right? So Huskies and German Shepherds are very popular dog breeds. Now, if I say that forget German Shepherd dog, I should not be forgetting Huskies. But what happens currently, if I say forget German Shepherd dog, not only Huskies, I will actually probably forget all breeds of dogs. That should not happen. That is the problem of fine-grained machine learning. So this is a problem and solution we proposed in CVPR 2025, and I'm going to talk about, again, I'll try to not go into mathematical details, uh, bare minimum mathematical details to explain you the problem and how do we solve it. So let's understand the meaning of fine-grained knowledge. So suppose we ask that forget Welsh Springer Spaniel, right, as a dog breed, right? So this is a particular dog breed, a very specific dog breed that I want to forget. So in the knowledge space, we have horses, we have apples, we have cats, we have golf balls, we have many other things, right? Many other classes. We also have Springer Spaniel, English Setter, Sussex Spaniel, and Cocker Spaniel as other dog breeds. Now, if I ask to forget Welsh Springer Spaniel, these classes, these concepts, model can very easily understand the discrimination power with the discrimination power of these foundation models. I can very easily say that Welsh Springer Spaniel is far off from horse, apple, cat, and golf ball. But in the feature space, in the embedding space, Welsh Springer Spaniel will be very close to English Springer, English Setter, and other Spaniels, right? Other dogs of breeds, because they look very similar. They are very close to each other. Now, if I say forget Welsh Springer Spaniel, we have seen, and it is very likely that I would also forget English Springer because the features are very similar. I'll also forget other Spaniels and English Setter also because again features are very similar, right? And that's what I highlighted, right? It's an example with golf ball, exactly same example with dog breeds, right? But ideally, I should be ensuring that these are retained, right? So again, just for the sake of example, so suppose if Rashmi says that forget me from your data set, like if it is understood that Gemini uses all our training data from Google Photos and others to train. Let's say this is the understanding, right? Now tomorrow with DBDP Act or GDPR, I can say Google, please forget me from your training data set and from your training model. So it should not happen that while Rashmi has asked to forget herself, my data should also be removed, right? I did not ask for it. I want to use the service and therefore I should be going ahead with that. My data should be retained in the model space, right? So this problem of closeness of different concept is called as fine-grained concepts, right? So if my target concept can have some certain fine-grained closely related concepts and some concepts which are coarse-grained, which are far off, which are other concepts which are like discriminate with the discriminative power. It's very clear, like okay, they are not close, they are very far off. And when I'm doing this unlearning, I should ensure that while I'm unlearning Welsh Springer Spaniel, I should not unlearn these closely related concepts as well as coarse grained concepts. I hope this is clear by now. Okay. Now, how do we do this? If I'm giving this image as a target concept, right? Let's call this image as a C of target, like CTAR. Okay, if I give this image and ask the model to forget this particular dog breed in the model space or in the knowledge space, I need to first obtain that on the data on which the model is trained, which of the concepts are closely related, right? So very first step we do is from the data set D, we first figure out the concepts which are very close to my target concept CTAR. Okay, so using a simple image encoder, I can obtain and go to the embedding space and figure out the distance between the CTAR to all the samples in dataset D and sort them. The samples which are closer to CTAR, they becomes essentially my fine-grained concepts, right? So all the samples that are closer to CTAR, I can pool them as a set called as A of CTAR, like adjacency of CTAR, right? So C target sample ka adjacency, all the samples which are adjacent samples, so that I should not forget these samples for sure, right? So they become my fine-grained set. Okay. Now, the remaining concepts which are like much farther away, they become my coarse set. Fine. Now, once actually you have this subset of what to forget, which is your CTAR, the neighborhood of CTAR, which is adjacency, all the sample set which we should not do a catastrophic forgetting, and a sample which is or the coarse set which is far off, right? Very, very far off. And again, we should not forget even those samples. Once I have this ready, I can fine tune the model with three losses. One is erasing loss, means that unlearns CTAR, that unlearns that particular concept. The guidance loss, which ensures that CTAR essentially, so I'll go to the details in the next slides. The guidance loss which guides that, okay, this is the space where you need to forget this particular loss, and the adjacency loss to ensure that this A of CTAR set is not forgotten, specifically forced not to be forgotten, these samples. Right. So the first loss is essentially a margin based separation loss, means that you have the entire knowledge space. Some sets are preserved set, which is essentially your D of retain sets, and your D of retain also includes your the A of CTAR, right? Means that is your adjacency or the concept neighbors. And what you do is, and we know what is my C of target set, right? A CTAR. I need to push this, I need to displace, I need to maximize the distance between my preserved space to the forget set. So I maximize, in fact, this is the loss function. I maximize my the distance between my entire space of retain, which includes the fine grained set, and the forget set. So need to maximize that space so that we forget it. We increase the distance. And once we increase the distance, the second loss, what it does is it pushes these all the target predictions or all the target forget set to something called as null anchor. Null anchor means it's like a I don't know what this class is, right? If I ask what do you mean by English setter or also Welsh Springer Spaniel, then it should say I don't know, right? So we create a null set or null anchor and push all these samples to the null anchor so that we truly forget the class. We don't remember the class altogether. Okay, so now if you see these two, what these two are doing, these two losses are doing. One, it is pushing this class, the concept that we need to forget, away from all the other classes and pushing to the null set, so that we can say that, I don't know what you are asking. I'll generate something which is a random image, but it would not be that particular sample. Okay, so these two losses essentially forces the model to forget a particular concept. The third loss essentially is a kind of a regularization loss, where we ensure that before and after training, all my concept neighborhoods, all my adjacency data samples should not change their characteristics. That the updated model and the original model for these concepts should be exactly same, right? And that's the adjacency loss, that we protect these ATARs to be forgotten, right? And therefore we avoid catastrophic forgetting. Okay, so jointly these three losses essentially then used to ensure that the model fine tune using these three losses ensure that while we forget a particular target, but don't forget the neighborhoods as well as the far off samples. Okay, now if I put the whole architecture together, the first step is figure out which are the concepts, right? So the concept neighborhoods are figured out. You obtain an adjacency set. Then you fine tune the model, and in our approach, we actually used LoRa fine tuning because we don't have the computational resources. Like we used 8 GPUs, 800 GPUs to train fine tune this model. We would need, if I have to really like go and do a true fine tuning, then without LoRa, then we would need about like 40 to 50 GPUs to do that, and therefore we used LoRa fine tuning to update the model space, which is only the which forgets the particular target concept while retaining the remaining ones. Okay, now if you put the whole thing together, this looks now very simple, and these three losses ensure that while we forget the target concept completely, to a very large extent, we also forget. We don't forget the neighborhoods, or we don't forget, or we don't do catastrophic forgetting. Okay. Now, once we build this particular architecture, the question came is that how do we say that actually our approach works, right? How do we evaluate it, right? Again, I'm assuming that in different lectures, evaluation mechanism must have been taught, right? How do we evaluate different foundation models or classification approaches, or medical applications? How do we actually do evaluation using MIOU or other matrices or accuracy other matrices? But if you have to evaluate unlearning algorithm, these standard mechanisms would not work, right? So intuitively, if you think of the objective function of unlearning, you have essentially two objectives, right? The first objective is, did I forget this particular class which I asked to forget? Let's say if I have asked my sample to be forgotten, then whether my sample is truly forgotten or not, like truly erased or not, and that is called as erasing accuracy. Did I achieve the erasing performance? So means 100% of erasing is good, right? And 0% erasing means I did not forget this particular concept at all. Similarly, the second objective was, from where I started with, that I should not be forgetting the samples, adjacent samples, or the neighborhood samples, right? So what is the performance on these adjacent samples? So the second accuracy should be adjacency accuracy. That did I forget any of the samples from adjacency or from the concept neighborhood? Means if I have an adjacency accuracy of 0%, means I have forgotten all those concepts, all those neighborhood concepts. If my adjacency accuracy is 100%, this means that I have not forgotten all those adjacent samples, right? Now I have two numbers, erasing accuracy and adjacency accuracy. And if I have to decide, let's say which is rank one, I can't do that using two numbers. I have to convert them into a single number. And that's what we have done with respect to proposing an erasing retention balance score, or ERB score, where we took the harmonic mean of the two performance, right? So ERB score is essentially a harmonic mean of erasing accuracy and adjacency accuracy. And higher the better, like 1 means the best performance, 0 means the worst performance. Okay. Now, using this particular metric, we used many fine-grained datasets as well as the coarse-grained datasets like ImageNet and I2P datasets to show that how much different models are doing versus our model is doing. So here is a performance set. Like we have existing methods where like fine-tuning methods or knowledge editing methods or distillation methods are there. Like these ESD, FNM, CA, UC, SPM, reseller. These are existing methods, and fade is our method. Like fine-grained unlearning is our method, right? So we called it as fade. Now, if you look at AER is your erasing accuracy, and A of ADG is your adjacency matrix, right? Adjacency score. Now, ESD or FNM, they are very good at forgetting a particular concept, but they are not good at retaining. Means they are actually doing a catastrophic forgetting on different data sets. The CA model is very, like, it's balanced, but then overall performance is not very good, right? And same with SPM. Reseller is very good at forgetting, but not good at and also very good at catastrophic forgetting. Should not actually do catastrophic forgetting, right? But the performance of 2% or 6% or even less than 1% on different data sets shows that reseller is not good for retaining the knowledge. And what we did was, like, if you look at our performance, it's like erasing is almost like 100%, 99.5, 99.6, or to 100%, and adjacency is also preserved to a very large extent, like 92s, 93s, like in the 90s. And therefore the balance performance, the ERB, the balance performance is also above 95% in most of the cases. And that's where, like, we show that is how improved performance we can achieve. The challenge is still with certain very close concepts, which are, let's say, again, in the case of dog breeds, if there is a husky German shepherd crossbreed. Now, if I'm forgetting husky or if I'm forgetting German shepherd, what happens to these crossbreeds? Right. Still there are like some challenges, but again, like to a very large extent, we have solved this problem. And my one of my favorite example is this last example of blue jay over here. If you look at very closely, if I ask a model to forget blue jay, there are many very closed um, concepts like Florida jay or green jay or cardinal, right? These are very close concepts of blue jay. So if I'm forgetting blue jay, existing models actually forget almost all the classes, or they don't even forget blue jay then, right? So like CA model is not even forgetting blue jay, whereas we were able to ensure that the knowledge is pushed, the knowledge goes to a particular null set, and that's where you are seeing this blurred output. With null set is essentially the average across all the samples that are there in the dataset, right? And that's why you're seeing essentially the average output, which is a blurred image, and not forgetting the other closely related classes, because the third loss, the adjacency loss, ensuring to protect that particular knowledge, right? Now, with this, like, means we also tried like other data sets, and then here are examples like forgetting the garbage truck, but other concepts are still retained, right? And then we have observed very good performance. In fact, now people are using this particular concept and the dataset protocols for showcasing their results and further improving. Now the target more is towards how do we ensure that 92% of the adjacency performance further improves to, let's say, 95%, 98%. Like how do we further go up in retaining the neighborhood concept? Okay. And we have also extended this particular idea to not forget only one particular knowledge. Let's say forget apple, then next time if I say forget orange, what happens, right? So now we call it as a like a continuous, like continual unlearning for foundation models. Like I can today I'm forgetting apple, tomorrow I'm forgetting orange, third day I'm forgetting violin, fourth day I am forgetting piano. So I can do this continuous unlearning without breaking the model. Like when there is a limit to which like we can do this, but then till what extent we can do. So now that's a third metric that we are proposing. This is paper under review, so I'm not going into the details because I can't share the paper with all of you right now. But then concept wise, what we are doing here is that can I the model will perform till what level of unlearning without the need of retraining. We are showing that up to 15 levels of or 11 levels of model unlearning one step at a time. Our approach does not break to a very large extent. 15 can still go 15, then we have retraining of the entire model. So there is a limit or capacity, or yeah, means in the simplest sense, limit to which we can unlearn the model to till that extent, right? So maybe I'll share the links of these papers for you to read and consume. One of the other paper that is still under review right now is where we have extended this problem to face recognition. Like if we have to forget in achieve that. So this paper is under review, so I'll not talk much. But again, like this is just to show that the same idea can be extended till for faces, which is actually much more fine grained, right? We all have eyes near eyes, nose, mouth, and most of the features are there. It's just the fine grained information which varies from one person to another person. So we are extending this we have network on. We are yet to work on video unlearning because computationally it's going to be very expensive. But we have so far extended to images, and within images, objects, now faces, and as well as in audio mode. Right, and then this is another challenge for students. This is something for you can look at. On Kaggle, we launched a challenge called as Genuine Challenge, where you can download a data set and run the foundation model and do unlearning of a model of like stable diffusion 1.4 and compare where you stand, right? So this is a challenge which goes on, and you can the first version of the answers we showed this in ICCV this year, but then this challenge is continuing. You can download and you can try this out on your own. By the way, the code for this particular fade approach is already available. I'll share the link with the organizers, and they can share that with all of you. Okay, so this was part one where we forget the classes, the concept. I have another 25 minutes before I start the Q&A, but are there any pressing questions right now? I can pause for a second or for 10 seconds and then see if there are any questions from the class or anything that you want to um, discuss on this particular part. Okay, if not, then let me move to the next part which is understanding the semantics, or the second part was, remember, means I talked about the incorrect compositionality structure outputs, right? So where the models actually fail to give the correct outputs, right? So this is like broadly called as understanding semantics of your prompt so that you can generate the correct outputs. Now, if you go to a doctor, let's say someone in your family got injured, right, or has any issues that needs investigation, and you go and see a doctor, right? So you ask the doctor, right, means what is happening, and doctor will actually explain you that the person has this particular symptom. These are the under this particular some catastrophic angle is also like blunting, and therefore this looks like a pleural effusion, right? So doctor will explain you certain concepts. At the same time, doctor will also tell that there is no evidence of certain symptoms, right? Like it right now, it is free of air detect, right? It may say that I'm ruling out the acute aortic dissection. I'm not seeing any bone fracture, right? There is absence of bone fracture, or the lungs appear intact with no sign of massive consolidation or cavitation. So the doctor will also explain that, okay, these are the positive or affirmative symptoms, and these are the negative or absent symptoms. And because of this combination of positive and affirmative, I'm reaching to this particular conclusion that the person is undergoing this particular issue, right? And then I'm pretty sure all of you have actually, means if you have seen a doctor, the doctor would have explained both like these are the things that are there, these are things which are not there, and because of reaching to a particular conclusion. Of like doctor to a lawyer, right? So a lawyer would also go to the court and say that my these are not the fingerprints of this particular person, right? Doesn't to my client, right? I have already talked about. I've already given you many examples, and just to like build again and recall those examples again. If I give a prompt, generate an image of exactly 5 red apples to the left of the vase with the flowers and 3 green apples on the right of the vase, no apples on top of each other. While it follows many of these constructs, there are 5 red apples. I asked for 5. It has created 6. Right? Green apples are 3. Right? Or probably 4. Yeah, there are 4 green apples. And I specifically asked that no apples are on top of each other. It the model may have just simply thought of like dropping no and apples are on top of each other means there is an apple on top of other apple, and therefore it has created that. So the multiple constraints the model is not able to satisfy, and most importantly these compositional fidelity constraints like no and not, they are not able to understand. Okay, even the counting they are not able to understand. You can try yourself, like you go to Gemini or chat gpt or your model of your choice and ask it to generate like 25 red cards and 30 blue cards. See what you get. Right, so I'll give you guys 15 seconds time to do this on your own. Right, you may have WhatsApp already, so go to Llama, right, Meta AI, and ask the Meta AI to generate an image with 25 red cards and 25 blue cards. See what you get. Right, and I'm giving you guys 15 seconds, 20 seconds to do that. Please do that. In the meantime, I'll just quickly get a glass of water, but you take 15 seconds to do that. Okay, so I hope you get that small exercise, and you must have realized by now that um, the model is not generating your uh, right. So model is not generating 25 blue cards and 25 red cards. Okay, yeah. So this is so jointly this problem is a compositionality problem, and it has multiple ingredients like counting, negation, spatial reasoning. These are all uh, ingredients of this particular problem statement. Okay, right. We have already discussed, so let me actually go to the next slide. Right, so 3 fundamental primitives. First one is counting, like precise cardinality, a specific count that we are asking for. Negation, which is like no, not, without, right, about absence of a particular concept. And spatial reasoning, which is essentially geometry or topology, layout, or physical plausibility. Right, if someone says that there is a femur broken in lungs, that's not possible, right? So spatially it is not possible, right? Or if I say that uh, my toe is broken in hand, right? It can't happen. So that's a physical implausibility. So spatial relations are also that way important, right? And so you need to look at different primitives, different fundamental primitives of spatial understanding. So the first primitive, let me actually run through primitive, and whenever the time stops, I'll stop there. But let me try to explain few primitives. The first one is like when we ask, let's say, generate an image of 51 raccoons, or like I asked the example to generate like 25 red cards and 25 blue cards. So similarly, I can ask the models to generate like 74 cookies or 56 panna cotta, and the models don't generate. And again, this is an example of Midjourney, Grok, Gemini, Sora, ChatGPT. All of them actually are not able to do that. There are a lot of duplication, merging, leakage, comparative errors. They all happen. And it has been shown that if as we increase the numbers, the target counts, the normalized error actually increases exponentially. So if you give a small number like 2, 4, 6, 8, it can still work. But the moment we go beyond 10, the error actually shows a drastic jump, right? And then again, like if I say that this is a radar plot highlighting that if I go up to, let's say, 10, the performance is still manageable. Like means if the number is 2, my accuracy is almost 100%. If the number is 3, again the accuracy is almost 100%. If I increase the number to 4, like any object with 4 count, I can still do that, means to 90% accuracy. But if at the moment actually increase the step size, we come actually to it less than 80% for number like 10. And if I increase the number beyond 10, the number actually comes drastically down. Right? And there are many CVP other papers and other conference papers that are coming in to solve this particular counting problem. Right? If I give an example, 11 cats and 9 dogs, this is what actually different models do. Right? So the way at least we have tried doing this is in a completely the two steps that we did. First one is like, how do we figure out that we are actually getting errors? Like means how do we measure that if I have asked for 11 cats and 9 dogs, um, I'm not getting 11 cats and 9 dogs, right? So how do we measure that? And that is the first step. And second, like how do we, without need of retraining, how do we in paint those more samples? So once we know that, okay, where how much error we have encountered, how do we fix it? Okay, so the first part was like, how do we create a metric of counting? Again, I'll try to be as less mathematical as possible to explain in a very simplistic way. So we say that, hey, no, means I get a prompt. From the prompt, let's say 11 cats and 9 dogs, we generate an image, right? So now from the prompt itself, we know exactly how much, what is my ground truth, right? So if my prompt is 11 cats and 9 dogs, I should have, my ground truth is what? Cats, the count of cats is equal to 11, the counts of dogs is equal to 9, right? So I should have for every object, so there are two objects, cats and dogs, and for each of the objects, I have number 11 and 9. Okay, now you use different object detectors like YOLO word object detector, or you use the retina face, or whatever your favorite object detectors. You use object detectors and run each of these detectors. Now you have, let's say, YOLO word or YOLO V8 or whichever your favorite detector is. You run it. You run this on this particular these samples, and then you get those bounding boxes. And each bounding box will be labeled as cats or dogs, right? So you extract all those bounding boxes, which has a confidence, and it also gives you a small number. Let's call that number as a confidence threshold. So if the threshold is above zero point 0.5, so whatever the model is saying, we'll trust that model is accurate. Fine. So we say that if the threshold is, let's say, the value confidence value is 0.6 and it says cat, let's say that this is cat and this is a bounding box for cat. Right now, I know that, okay, this particular, let's say, YOLO V8 has counted cats 7 times and counted dogs 5 times with a confidence threshold of 0.5. Now I know that how many cats and dogs are there in this particular sample. I'll compare with my ground truth. I'll then calculate the relative error, right? And I'll repeat this for all three detectors. So let's say my detector 1 says that 5 cats and 5 dogs. Detector 2 says 3 cats and 5 dogs. And detector 3 says 5 cats and 3 dogs, right? I'll calculate the total error, the total average error across these three models, okay, for every object. So my relative error for every object essentially is a number ranging from 0 to 1, right? So how much error, overall error that we have encountered. So that is again very basic, like based on the counting, trusting that whatever is director is saying is correct. We simply go ahead and count those numbers and compare the numbers and say, okay, you are saying that zero point 0.7 means I'm 70% accurate, right? So 70% of the times I'm able to generate the correct numbers, 30% error is there. right? So total final score will become essentially the average error across all the three models that are there for that particular sample. Okay. Now, since I have to push this into a 0 1 format so that I can understand it better, like we always understand 0 1 better. So 0 minus 1 minus average error becomes my metric. So whichever is higher, I just go with that. So means the error cannot go below 0, right? And then or the accuracy cannot go beyond 0, below 0. And the maximum that actually you can obtain is 1. Like if whatever you asked for, let's say 2 cats and 2 dogs you asked, and you are able to generate 2 cats and 2 dogs, so the maximum performance that you can obtain is 1, right? So that's why it is in the range of 0 to 1. And whatever error that you are actually encountering, the average error across three models, that becomes the average error that you subtract from max, right? So let's say here is an example. Director 1 finds, so I'm expecting 5 cats and 3 dogs, let's say. Director 1 finds 4 cats and 3 dogs. Director 2 says 5 cats and 2 dogs, and director 3 says 6 cats and 3 dogs. Right. So ensemble count essentially is 6 cats. Right. So 6 plus 5 plus 4 divided by 3. Right. So 5 cats, and 3 plus 3 plus 2 divided by 3, that becomes 2.67 dogs. So relative error for cats is 5 minus 5 divided by 5 means 0, and 2.67 minus 3 divided by 3 is equal to 0.11. So my NPS is essentially that I'm able to generate 94.5% accurate results. Like means my output performance is 94% or 0.945. Right. So again, it's a very simple method to just do the counting. The problem with this approach is that I'm assuming that anything above zero point 0.5 confidence is correct, right? And therefore, if I'm generating an output which is 0.945, this means I assume that the model, the three detectors that we used, they are able to detect it correctly, and the confidence of 0.5 is correct. So we are dependent on particular confidence threshold. Now, in order to minimize that error or minimize that particular impact, we proposed one more step and incorporated the confidence also. But for the sake of simplicity, I'm not going into the details of how did we include that. But what we also did was we thought humans also do in the similar way, right? Means we say I'm 90% confident that there are 5 dogs and 3 cats, right? So what if we compare with humans? And that's what we did. Like we replaced our detector with humans, and we asked the humans to like say that how many cats and dogs are there in the image, and compared with the NPS. And that actually showed that means that the proposed approach of counting is very close to how humans do counting. And so the performance is actually very close to humans versus the this kind of approach of ensemble counting. Right. So that actually showed to that this approach of evaluating the counting error is the correct way of going about it. Right. Now, the question actually comes in, then can we achieve the precise numeric count without the need of retraining? How do we do that? Right. And that's where we proposed a training free mechanism. And this is computationally expensive, but it does not require any training. Right. And we call it as a NURAG, like training free retrieval augmented generation. Again, I'm not sure if RAG has been taught or not, but again, for the sake of simplicity, I will not go into the details of the algorithm. But what we did was essentially 4 steps. Simply, I will explain in a very simple way. What you do is like you take the particular prompt. LLM will parse the text prompt. From the text prompt, let's say I say 5 dogs and 3 cats, right? So now I know that I need to have space of 5 dogs and 3 cats. So I create a draft layout where 5 dogs and 3 cats can be generated. Right, that much space is there, and then we mark those areas where dogs and cats should be put in. Then from the memory, we figure out like okay, what the dog should look like, what the cat should look like, and those should actually go back into those particular in paint those targets into those particular spaces. and we repeat till we get 5 dogs and 3 cats, right? So this becomes essentially a kind of inventing method where we retrieve from the knowledge and paste it in that particular layout space, that okay, till we will keep on pasting dogs, like generate a sample, generate one dog and paste it, generate another dog and then paste it, in a smooth fashion. Obviously, means we need to ensure that the quality is also maintained. So in the draft layout, we keep on putting those numbers of dogs and cats, without the need of retraining the entire model. Right. So again, this is very simplistic way of explaining. There's a lot of maths behind it, advanced maths behind it, but this is how actually we did achieve this maximizing the counting performance. Okay, and we could actually generate, let's say, 88 golf balls, or 42 fire extinguisher, and if I have to generate, let's say, 18 loins and 2 golf carts. So I'll take this example of 18 loins and 2 golf carts. So we first created like a draft layout saying that there should be 2 golf carts, and then there should be 18 loins in this image, right? And created what are the possible locations that loins and golf carts can place in. And then one at a time we start pasting. We generate one loin and paste it. We generate 2 golf carts and paste it. And that's how we kept on doing that, right? And that's an iterative mechanism. It's costly, it's expensive, but as I said, like, it does not require the model to be retrained. So I can use stable diffusion, I can use flux, I can use anything to actually generate the correct outputs without the need of retraining. Okay, how much time do I have? Okay, so I'll stop here. Means we prepared the data counting data set with 1600 objects, and then we could actually generate. Our performance is very high when the object counts is about like 1 to 25, right? We are about like 85-90% accurate, but still, up to 50 also we are able to do about 70% accurate. But then beyond 50 still is challenge. We are still evolving the method to further improve, but that's a research challenge that we are working on. So higher the numbers, it's more complex, and that's where the current research is. And with that, I will stop here, and I'll see if there are more questions. Um, I'm not able to finish like last 10 slides, but that's okay. We can stop here and take more questions now. Take questions from all of you guys. So are there any questions from the class? Okay. Okay. So then I can take another 5 minutes to or 10 minutes to finish the remaining 10 slides. Let me do that very quickly. Huh, let me do that. Okay, so the second primitive was negation, right? I talked about how do we manage the failures of not, right? Means how do we avoid shortcuts, because I don't look at no altogether, right? Negation markers altogether. So when we started working on this, we realized that there is no like data set to work on it, because generally people don't work on negation, right? So that's what we thought. The very first task should be like create a data set of like a dog that does not have ears, a car without tires, right? A ball of ramen with no chopsticks. These kinds of negations that we realized there was no data set. So we first started creating the data set. For that, we first needed to understand how many types of negations are there. And at least before starting the research, I did not know that there are like 5 types of negation. And then when we started, we realized there are syntactic, morphological, lexical, semantics, non-verbal. Like if someone says that are you eating anything, and if you're really eating something, then you will not speak, right? You will not be able to speak. You will actually give some non-verbal cues, right? And many times we just shake our head, right? In no. So how do we, or just raise our hand to stop? Like if you're crossing the road, you shake your hand and say that stop the car, right? So how do you enable negation for verbal, non-verbal, textual, audio, right? All different kinds of things. While we focus mostly on textual negations in our research, but then we have started working on the audio negations as well. Right? And there are many negative words like a dog does not have ear. At the same time, I can have generate a painting. Don't use the red color. Right? That's what. Let's say if you go for a painting class, your instructor can say generate a painting, but don't use the red color. Or you can have generate a picture of a Christmas scene. If it has a Christmas tree, don't add ornaments. Means it's a conditional then, right? So these kinds of negations are also there. Like you can have a visual feed saying that don't feed the ducks or don't feed the animals, right? So these are essentially negation of different kinds. In order to create the data set, we needed to understand these negation types. And again, the first part was that how do we measure that it does not understand, and it does not understand no, right? It can be bias, it can be different factors, language. And how do we figure out that the model does not understand a no? So like here is an example, like the image of a 60 individual in a crowd, all are Indians and no one with dark skin tone, and 50% male and 50% female. How do I know that means the model actually has followed all the instructions? Right. And if I extend this to Hindi, let's say, or any language, any words language, then how do we know that it has understood that the language as well as the context, the semantic context, right? भीड़ में 60 व्यक्तियों की छवि, सभी भारतीय हैं, किसी की भी त्वचा का रंग गहरा नहीं है, 50% पुरुष, 50% महिलाएं हैं, right? So this is the same sentence in Hindi, and the models just actually give different outputs altogether, right? Both Gemini and Grok here in this example. So we created actually a negation evaluation framework. And it's very hard if you think of this way, something which does not exist over there in the image. How do we measure it? Right. So if I have an image, if I have a prompt like a book signing with unsigned copies where the tables are unarranged and the readers are uninterested, I generate an image. How do I know that this image is correct representation of the prompt? So what we proposed is that why don't we actually split this particular prompt itself to 5 questions. If there are 5 concepts, we can generate 5 questions out of this particular prompt itself. For example, are the copies signed? Are the tables arranged? Are the readers interested? Is this a book signing? Is any book being signed? Right? Now, I have converted my prompt to questions. From the questions, I know the ground truth. What is my ground truth? Are the books signed? From the prompt itself, I know it should not be. So no. Are the tables arranged? ID means ground truth is no, should not be based on the prompt. Right? The reader is interested. Again, from the prompt, it should not be. It should be no. Is the book? Is this a book signing? My concept should be yes. Like based on the prompt, it should be a book signing. Is any book being signed? Right? Again, because of the prompt, it's unsigned copies. I should be saying no. Right now, what has happened? So I can use a foundation model, let's say OpenAI's foundation model, to evaluate and find the answers to these questions. So this becomes essentially a problem of visual question answering. Give an image, give a question, it will give you an output, right? So are the copies signed? No. So and the ground truth is no. So this means one correct answer. Are the tables arranged? My VQA says that the tables are arranged, whereas my actual prompt says no, table should not be arranged. So it's a conflict, right? So similarly, like then you answer all these individual questions and you figure out how many times you have actually answered correctly. Like the image that is generated is matching with respect to ground truth or not. Like in the first example, like a fitness gym with no treadmill running, where the weights aren't lifted and there are no trainers coaching, all the conditions are met, right? Whereas in the second example, only 2 conditions are met and 3 conditions are not met, right? Negation have been failed for 3. So overall, my negation accuracy is what? 70%. Out of 10, 7 times I'm correct, 3 times I'm not correct. So my negation performance is 70%. And here is a baseline for stable diffusion, GPT, and Grok. None of them across these syntactic, morphological, and lexical kind of negation types, none of them even actually crossed 75% accuracy. This means that these models don't understand negation beyond like 60-70% performance, right? So this is again like a major problem. And with this kind of benchmarking, we highlighted that these models don't understand negation at all, right? Now, with that, I would stop over here, and I would acknowledge my students who are the contributors of this particular work. The journey continues. This is a continuously evolving research area, and I would wish you all the very best for happy coding for generative AI. If there are any questions, I'll be happy to take questions. Roshni, is there any questions? Okay. Yeah, please. Okay. No worries. So thank you again, and I'm really sorry I could not come in person, but hopefully something you'll take something out from this particular school, and wish you all the very good luck.